Like the teacher said, I'm Dan. I work for Portland General Electric, and I'm going to talk to you a little bit today about what an engineer does and how some of the things you're learning in your class might apply outside. So my goal for today, what I hope to communicate to you is, like I said, talk to you a little bit about engineering. I want to tell you a little bit about my story, how I got involved in engineering and ended up to where I am today. How your class subjects might relate to some of the work that we do at PGE, and how they might relate to outside of the classroom. And if you have any questions, go ahead, raise your hand in the middle of the presentation. We can stop, we can talk about those. If I don't see you, hey Dan, I got a question, let me know and we'll talk about that. So, the introduction. Like I said, my name is Dan, and I'm a mechanical engineer for PGE, or Portland General Electric. Is anybody here familiar with PGE, know what they do? Yeah?
They work with the water and try to make it clean.
Yeah, so we actually are the electric utility in a good chunk of the Portland area and the surrounding suburbs. We create the electricity that keeps the lights on in your classroom. We have a number of different power plants in the area that we maintain that generates the electricity, and we have the transmission lines that send those to houses, to buildings, to your school here, and actually keep the lights on for you. So specifically what I do is I'm involved in the power plants themselves. I work with maintenance and upgrades on those. So I try and make sure that the power plants are running, they're running efficiently, so that you guys can continue to get electricity, and it's cost effective for the people that buy the electricity for us. So why am I here? Like your teacher said, sometimes you learn this stuff in class and you're kind of like, what am I ever going to do with this? How does this relate to anything that I do in my daily life? And I got to say, science, technology, math, all that stuff affects your daily life a lot more than you sometimes realize. Math, chemistry, physics, all that stuff keeps you warm. It keeps your TV on. It gets you to school. It does a lot of different stuff for you. And I hope to today kind of explain a little bit of how that does impact you outside of the class. So, first question, what does an engineer do? The technical explanation for what an engineer does is the practical application of science. So what the heck does that mean? That means that outside of the classroom, when I'm in my job, I'm actually taking the stuff that I learned in school, the science, the math, the physics, all that, and I actually apply it to what I do in my job and in what I do to make a living. Engineering design is very important in our daily lives, and I think sometimes it's very obvious, sometimes it's not so obvious. The roads that we drive on, the building, the school here, an engineer had a hand in that. The devices, the computers that you use, all that stuff. Engineers are involved in that. Engineering design is part of that process. So as an engineer, a lot of times we do design and we do testing. So if we want to create a new product or do a new process, we'll actually go through the design part of that. We'll actually look at what we want to do and try and put it down onto paper. Try and explain that, draw it up, so that when we actually try to apply it, we have a base for starting that. If you wanted to design a new tool, you wouldn't just start making a bunch of them trying to sell them, right? You'd write up kind of what you wanted that thing to look like. You'd probably make some drawings, you decide what materials it might be made of, what size it's going to be. All those questions are part of the engineering process. When you do get a design that you like, you would do some testing, right? You'd make sure that it's going to work in the way that you wanted it to, and you're going to try and make sure that it doesn't fail. Unfortunately, sometimes things do fail. But the thing about that is that failure sometimes leads to improvement. When things go wrong, we can look at why they went wrong and try and improve them. So, let's watch a video.
Narrows. From the day it was finished in 1940, it bounced around. Dubbed Galloping Gertie.
So I'm assuming nobody's been on a bridge that's ever done this before, right?
What?
Real trouble started the day it began to twist. The wind wasn't particularly strong, but it stayed steady. Each time it twisted, it turned a little more.
Right, so there are a lot of engineers and designers and builders that built this, and unfortunately it didn't behave the way that they wanted it to.
Finally, it twisted itself apart.
Doing something like
and
this for
became
long
every
enough.
bridge builder's nightmare.
That was retarded.
So this is actually what the bridge looks like today. Now, the thing to think about is that, yes, unfortunately that bridge failed, but because of that, because people went back and they looked at that, yeah,
Do you think the people that died, like their families got paid or something?
I actually don't think anybody died. I think that because it had such drastic movement, that they kept people off of that bridge. There were a few shots where there was a car and there was a guy walking on it. But fortunately enough in that situation, they were able to say, hey, this is a dangerous situation, let's get people off of here. So I'm sure that if that, and that has happened, bridges have collapsed, and I'm sure that's part of it. But in this specific instance, I actually think fortunately enough, nobody did die. If there was any injuries or casualties, they're very low, fortunately enough. But one of the things to think about on that is that unfortunately that bridge did collapse. We were able to go back and look at that and say to ourselves, okay, why did that happen? And do testing and look at all the different aspects of that whole scenario. And now, not only are we able to have the bridge built now and have it stand and not have that, but we can take what we learned from that situation and apply it to other bridges throughout the country. So unfortunately failures do happen, but that's part of the process of improvement. So, kind of to build on what we were talking about with what engineers do, what specific type of stuff might an engineer do? And this applies to other types of engineering, not just mechanical engineering. This right here is the natural gas plant that we're building in Eastern Oregon right now. And you see there's these large cranes that relative to the size of this actually look pretty small, right? We have 800 or so people on site doing construction every day. That's a lot of people, and so we need engineers on site that can not only understand the processes involved, but manage those people and make sure that the construction's going properly. We have engineers go in and they actually inspect what's being installed to make sure it's done properly. So we look at the whole process of designing this plant, putting it down onto paper, purchasing all this and actually installing it and getting into a situation where we can run and operate it in a safe manner. Equipment design. This is another thing that engineers can get involved in. So that plant had a lot of different pieces of equipment, right? So somebody had to actually go and design all those pieces of equipment. This is a pump right here, and what you'll notice is this isn't a photo, this is a 3D rendering of it. So there are actually engineers that work with modeling software, they work with computers. They actually develop, they design all the specific parts, and they put it together in a virtual space so that they can make sure that it all fits up and all the pieces can operate and do what they want to do. They can actually simulate operation in their programs and figure out how much flow is going to go through. And so it's very important that we have engineers that can design that. We want to put this onto a piece of paper or virtual space so we can visualize it. Then we might build a prototype, something that we can test, something that we can make sure that, hey, what we wanted to do, can actually do that. And then at that point, you have a product that you know will work, and then you can mass produce it, you can sell it. Engineers get involved in manufacturing. Once that design, that prototype is built and we know we can start building it, now we can actually go out and build a bunch of them and start selling them because we have a good product that people want to use. This is a car assembly line. There's a lot of different machines, and so there are engineers involved in that process too. Not only the design of the car, but the design of the machine that assembles the car. Engineers can also look at the manufacturing process itself. As these cars go down and the pieces are assembled, we want to make sure that we're doing that in an efficient process. costs down, it'll make it just overall easier. So that's something that engineers might be involved with too. Unfortunately, as we said, sometimes things fail, so engineers sometimes get involved in evaluation and investigation. When something goes wrong, we want somebody to come in, review it, and say, okay, why did this fail, and what can we do to improve that? The picture on the left over here is an electrical fault. This current is going from one wire to another wire that we don't want it to. And this is a very dangerous situation. You don't want this to happen. Not only can this damage equipment, it can hurt people. And so when something like this happens, we want to review all of this and understand what was going on in that situation, why it failed, and think about what we can do to make sure it doesn't fail again. So engineers get involved in that. The picture over here on the right is a building after an earthquake. And we design our buildings to withstand natural disasters, but sometimes those buildings fail. So when this happens, not only did we have engineers that were hopeful can design a building to withstand that, but when something like this happens, we want somebody to come in and do an investigation and figure out why did this happen. Any questions so far? Okay, well I'm going to tell you a little bit about my story and how I got to where I am. To start off, as a kid, I liked to tinker with toys and pieces of equipment and whatnot. So anytime I got a toy, I was almost as happy when it broke as when I got it, because that meant I could tear it apart and see how things work. So I didn't understand any of the internals, how any of this actually worked, but I like to look in there and see it. So I kind of had that feeling at a young age that, hey, this might be something I'd be interested in. It's not necessarily the case for everybody that gets into engineering, but that's what I enjoyed. So then going into high school, which you guys will be doing soon, I kind of started to think a little bit, hey, what might I enjoy doing once I actually get out of school and get into the workforce? And so math and science was something that I tried to focus on a bit in high school, which you don't necessarily have to do, but that's something to consider. One thing I did want to mention is that to be an engineer, you don't have to be a math or a science whiz. I was not very good in chemistry. I'm still not very good in chemistry. That's something that I've always struggled with. But if you struggle with the class, if there's a topic that you struggle with, it doesn't hinder you from doing something that you want to do if it's engineering related or any other type of field. But what you guys are doing now is you're building the foundation, a good knowledge base, so that when you go on to the next step, you can build on that. And so it's sometimes tough, but I would strongly recommend keeping up with the work that your teacher provides. It's not just to keep you busy, it's to give you a good knowledge base for when you go on to high school and possibly college and even further on that. So I went to Purdue University, that's in Indiana. I'm originally from the Midwest. And I got my bachelor's degree, which is a 4-year degree. So I spent 4 years in school doing various classes. There were core classes, which are the classes that apply specifically to mechanical engineering and engineering in general, as well as electives, and I'll jump into those a little bit further along. Also involved in the schooling is typically, and this is not just for engineering, but a lot of different fields, you'll do internships. So when you get into college and you take your college courses, you'll have summer breaks, and typically you'll go to a company and you work for them for a short term. It's a great way to get a feel for what it's like to work for them, what it's like to have a job in that industry, and you can kind of figure out whether or not it's a good fit for you. After I got out of school, I spent a few years in nuclear power. So I actually jumped right into the power industry and I started working for a company that does work with nuclear power plants. After that, I started working for Portland General Electric, so I've been in the power industry my whole time outside of school. So, why did I choose mechanical engineering? Like I said, the nuts and bolts of how things worked was always something I was a little bit interested in. I always liked machinery and moving parts and big things. Electricity, chemistry, that stuff that's not really very spatial just wasn't kind of my cup of tea. Not that it was anything that I actively disliked, but it just wasn't for me. So that's why I moved towards mechanical engineering. Like I said, chemistry was not a strength of mine, so I did not become a chemical engineer. And then, there's a few things to consider as to what do you want to do and what industry do you want to work for when you get out of school. I personally didn't have any specific field. You guys might have something specific that you might want to do when you get out of school. Computers or cars or planes or something like that, work in that field. But I didn't, so I felt that mechanical engineering had a broad range of industries to work in. So some college courses that I took, thermodynamics is the study of heat and energy. And your teacher tells me that you guys just did a topic on that, so that's really expanding on that knowledge. Something I like to say about thermodynamics is understanding why when you put heat to a pot of water it boils, and specifically what's going on in that reaction, and taking that and furthering that out into how you can really apply that to some interesting ways in industry. Fluid mechanics sounds fancy, but it's really just the motion of water, if you will. It's any type of fluid, but why something at a higher elevation or a higher pressure is going to move to a lower elevation or a lower pressure, and figuring out how that's actually going to interact. Material science is looking at the various types of materials that we use all the time. Why roads are made out of concrete, why buildings are made out of steel. There are different aspects of different materials, and you can really get involved in specifically how those materials work. Electricity and magnetism, something that you guys are going to get into. So even as a mechanical engineer, I was taking electrical engineering classes. Well, that came up again. I had to take chemistry in college. That's not good. I didn't enjoy that too much. But I still took it because you have to have a wide knowledge base. You want to be able to make sure that you get into a bunch of different things, and when you guys get onto further schooling in high school, possibly college, you'll see that you want to broaden your knowledge base. Math, physics is also a part of it. Sophomore and senior design, I actually got to design and build some prototypes. We actually, as a team, made a device that helped people change a flat tire on their car. So not only did we get to design it and put it onto paper, put it into a computer, but we actually got to use some of the machinery on the university campus and actually build that and get to use it, and we filmed it, and it was fun. Then there's some not so obvious courses that you guys want to take, or you have available to you when you get into college. You don't have to just take the courses for your specific major, what you want to get into. So I got into things like engineering ethics, safety design, making sure that we're thinking about people when we're doing engineering work and not just trying to make a machine that does something. We have to consider how that impacts people's lives. Maybe also ideas of, not stealing other people's ideas and going through that. So nothing very technical related, but still part of engineering. Philosophy, English, history, all those things that don't necessarily relate directly to mechanical engineering or engineering in general, but stuff that's still interesting, stuff that if you have a passion for history or if you have a passion for writing, you can still do all that stuff and still study something else. And then, some other fun courses. Foreign language courses are big. I even took a bowling class. There's a lot of different things you can do in college. There's also some great universities here in the Northwest. Oregon State University has a great engineering program. Portland Universities, Portland State, University of Portland are great ones. The Northwest has a lot of great ones. University of Washington has it's a great school. Washington has great schools. And so, lucky for you guys in the area, you have a lot of great universities nearby. Any questions before we jump into some examples of how what you use in the classroom applies outside of the classroom? Okay. So, take a look at these photos. So this is a heat exchanger. Right, so this blue piece here, it's got a cylinder, it's got a blue piece back here. This is the same piece of equipment that we installed last summer. This was at the start, then a little bit further along in the process. and what it looks like today. Does anybody see any difference from 1 to 2 to 3 yet?
You put something on to put like something over it.
This?
Yeah.
Yep. And then down here, you see this? Oh, it's wrapped in something down here. Anybody have any ideas of what that might be? Yeah.
Insulation.
You got it. So this is, there's cold, 60 degrees, air temperature, natural gas coming through. It comes through the top, it comes out the bottom. And then we have hot water that comes into from one pipe and interacts with it. It doesn't mix, it interacts with it. And it comes out this other pipe. What we're trying to do is we're trying to transfer the heat from that water to that gas, right? So we don't actually mix them, but we put them in close contact with a material that can transfer heat very easily inside of there. Anybody have any ideas of why we might want to wrap that around the heat exchanger? No.
So,
Yep. Yeah, if we have this heat exchanger, we're trying to get the heat from the water to the gas, and it just goes out of the side of the machine, it gets lost. What ends up happening is this becomes a less efficient process. We have to use more water to heat it to the same temperature. So that insulation is real important. And so I believe that that's pretty similar to some stuff that you guys were working on previously. So we use insulation all the time. One of the interesting things too about this picture is this red cable here that might be hard to see in the back there. That's actually what we call heat trace. That's a cable that sits inside of the insulation. We run a current through it, and its whole basis is to generate heat. So we actually use electricity and we put heat into this, and then we wrap it all on insulation. So maintaining that heat and making sure that that heat transfer goes where we want to is really important what we do at PGE and other electric utilities. So, heat transfer, how does it relate to your parents' car? So this diagram here on the left is just a very simple example of how we transfer heat from one place to another without mixing. So think of this as a tube or a copper tube or something. It comes in, there's a cold water coming in, and it goes down and it sits inside of this hot water down here. And you're not mixing, but you're actually transferring the heat over through that material, and it comes out as hot water. How that relates to your car, your engine block, what's going on in there generates a lot of heat. And if you keep that heat in the engine block, you can get a lot of problems. Things go wrong, things break, things fail. So you want to get that out, right? So we put cold fluid in there and we run it through the engine block. Similar to this, we're just trying to get that heat from the engine block into the liquid. And when the liquid comes out, we pull the heat out of here and we have it here. Now the problem is that we have hot liquid, we don't have anything to do with it. So what we do is we put it through the radiator. We put it through another heat exchanger, and we blow air across it, and we push that heat outside. That's a situation where we want the heat to leave the car. We want it to get away from the car. So, I mean, you know, transferring heat, trying to make sure heat goes from one place to another is really important, and it affects a lot of different things in your daily life, sometimes that you don't even realize. This is a pretty complicated diagram, and I wouldn't worry too much about the specifics. I'll point out what I think is real interesting. This is a gas turbine, right? So think of an airplane engine that's sitting in place, right? We suck in air, we draw air in, and we put in gas, and we mix that air and we mix that gas into the right mixture. Then we ignite it, and that gas expands, right? And we can use that. And what happens is that gas goes out the back end, and if we didn't do anything else, it would just shoot out and it would transfer, it would dissipate out to the atmosphere, right? The problem is we have all that heat, and we're just getting rid of it. We're just throwing it out there, and it's just going away. We're not doing much with it. And so at some point, somebody looked at that process and they said, hey, I've got a good idea. I'm going to take pipe filled with water, and I'm going to run it through that exhaust gas path. So I'm going to heat this water, and I'm actually going to boil this water. and I get it really, really hot. And that's going to create steam. And what I can do then is I can pass that water through a steam turbine. That's the steam turbine down here. So what they're actually able to do is take this heat and utilize that energy down here and actually generate more electricity just using this exhaust gas. So again, that heat transfer is real important. It makes this a much more efficient process. And then on top of that, that steam comes through. We pull all the energy out of that steam, and it's still steam, but we want water going through here. So what we do is we do another heat transfer. We have a condenser in the back end here. It's the same thing. It's tubes of cold water this time. And so we put that steam over those tubes. Those tubes actually transfer that water from steam, put that into water, and we can reuse that water. So we can take that water and we can keep reusing it. So it's all transferring heat from one place to one place to one place. So again, heat transfer is very important in what we do to generate the electricity that you guys use. Alright, let's jump to motors and generators. Another video.
And now let me.
Trying. Alright, so let me get it to the better spot. Okay. So this device here, this measures current. Think of this as just measuring the electricity in this that's going through it. So what this guy has done is he's taken a copper wire and he's wound it around into a circle, right? And he connected both ends. So you have a loop that runs through this machine and that runs through the coil, right? Now what he does next is this is a magnet. Right? So he has a magnet in his hand. So all he has is copper wire and a magnet. He has the device hooked up to see how much current, how much electricity is going through. Now watch the needle. As he pushes it through, that needle moves. So all he's doing is taking a magnet and a copper wire, he's creating an electrical current. Another video. So similar, we have the copper coil, we have a magnet, now we're putting current through it. As soon as we get this spinning, now we can use that electricity to create motion. Kind of neat, man. Yeah, it's just a magnet. I mean, you could do this very easily. This is the idea behind the motor. So we take electricity and we actually can create motion using that electricity. We use that to spin rotors on pumps and all different pieces of equipment. One more, which I hopefully can tie together to what we've seen, and then we can talk about it a little bit. So what he has in his hand right here is another copper coil, copper wire, round, lots of turns on that, all lined up there, connected together. In his other hand he has a magnet. Has anybody ever taken two magnets, tried to push them together and they repel each other?
Yeah.
So magnets, if you think about magnets, they actually have a field around them, a magnetic field around them. So they can interact without touching things around them. And so what he has is he has this copper wire and it goes through an LED, little light bulb. And what's interesting is, just passing that magnet near the coil, he can actually get that light to light up. So he's actually generating an electrical current through that coil. That's essentially a demonstration of Faraday's law. If you have an interaction of a coil, to put it simply, a coil with a magnetic field, you can generate an electrical current. And he does this and he demonstrates that you pass by, on one side it works really well. If you go underneath, it doesn't work as well, but it still works. So the orientation is very important too. What I wanted to show you is the fact that just something very simple as a magnet and a coil can generate electricity. So you'll probably learn about that at some point and you'll say, okay, what does that have to do with anything? That's how we generate electricity, that's what keeps these lights on. So this right here is a turbine in a hydroelectric plant. So if you can imagine, so these can get really big. This is a guy right here, and this is a big piece of machinery. So we're taking what that guy was doing and making it on a very, very large scale. So high water over here, low water over here. We have water flowing across here. We put what is essentially a boat propeller right here. So what that'll do is the water passing through will make that spin. That we attach to a rotor. And for our consideration, we attach a magnet to the top of that. And we have, along the edge here, stationary, not rotating copper coil. So we have that spinning, that moving magnet, and we can actually generate electricity using that water moving from a high ground to a low ground. And that's how that works. How about the wind turbines that you guys might see driving around if you go to the eastern part of Oregon through the gorge? You might see wind turbines. Any different? Yeah, it's just we're using wind instead of water or steam or gas. So we have the propeller here, and as the wind goes by, it moves that propeller around, spins the shaft. We have some equipment here, gearbox, gears that transfer and do all this fun stuff, but at the end of it, we just have a generator on there. It's the same process, it's just in a different orientation using a different source of energy. So to kind of pull all this together, we generate heat, we have some energy source, right? And a lot of times we have a transfer of heat. We have that exchange of heat from one place to another, and we control that. We want to make sure we do that as efficiently as we can. And when we do that, we can take, say, water, and we can boil it, and we can create steam. We can pass that steam through a steam turbine, which then spins a rotor, and we can turn this magnet around inside of this and actually generate electricity using Faraday's law, or using stuff that you learn about in school. From that, we connect that, we send electricity to your homes, to stores. So that's kind of how we take some of the stuff that you are going to learn about or learned about, we actually apply that outside of the classroom, and we keep lights on for you. Any questions? Got a couple of extra slides to show you. This is all kind of stuff I get really interested in, like talking about it. So, how a steam turbine works. So I talked about those, and you're kind of like, well, what the heck is that? I like this picture right here. Anybody seen a tea kettle put on the stove? What happens? You get steam shooting out, right? So if you direct that steam on, let's say, a pinwheel, that's going to make it spin, right? So what we do is we generate a lot of steam and we control that, and we push that through, and that actually has essentially a pinwheel or a propeller, if you will, that actually spins the rotor, and that spins the generator, which creates the electricity. So this is kind of another diagram to kind of show this. We have steam coming in, it spins this, and it spins this generator, which uses that, Faraday's law, magnet moving around the coil to generate the electricity. If you look at this guy right here, these are big pieces of machinery. This is a steam turbine in one of our plants. And this is disassembled right here. We actually pulled this apart to inspect it, to fix a few things, and make sure that it would continue to run for another 10, 15 years. So when you think about this, there's a lot of people involved in this process. There's a lot of people involved in pulling this apart, making sure that it's done well, getting everybody prepared, the management up front, getting people lined up to make sure that they can get this all done in a timely manner, in an efficient manner. I was talking to the class before you guys, and there's some other people involved in this, in getting this all done, people that work for PGE. It's not necessarily engineers that work at this plant. There are technicians, there are people that work with the nuts and bolts and pulling things apart, welding, grinding. There's a lot of community colleges in the area that you can go to and you can learn a lot of that stuff. There are people on site that handle purchasing products and doing all that work. We have a legal department that works for us. So if any type of contracts or anything comes up on those, we actually have people that work with the power plants to make sure that all those contracts are in place. We have an environmental services group. We have people that work with the wildlife, with rivers and streams, with hydroelectric plants. We want to make sure that fish can pass through, they can go downstream, they can come back upstream and not get involved in any of the equipment we have. So we have a lot of people that work in related fields, in science fields that aren't necessarily engineers. So there's a lot of different opportunities out there for people to get involved in the power industry or any industry. Another cool photo. So you remember the generator, the copper coil that the guy had in his hand. Well, this is our copper coil in one of our machines. So these guys standing here, I mean, this is a big piece of machinery. This is 90,000 pounds. So just working with this, you can get into some interesting stuff, but it takes a lot of effort to do that. There's a lot of technical aspects, but it all comes from a good foundation of knowledge at the start of your schooling. So. Any questions? Yeah.
What position do you play in the company?
So I work as a mechanical engineer, and I work in the headquarters that we have in Portland. And so my work group specifically supports all of our power plants. So we have engineers that work specifically at the power plants. They work there every day. They maintain the equipment. They're involved in the day-to-day operation. I'm involved in the engineering group that supports them, and anytime they need to replace a component or they need to upgrade something. So if there's a new technology out there that, hey, we can apply this to our power plant, and it'll help us run more efficiently, produce more power, then I actually get involved with the project management side of going out and finding that technology, making sure that it's going to work well in our power plants, and then actually go through and coordinate the installation of all of that. So there's a lot of different aspects that come into play. As a mechanical engineer, I still get involved in water chemistry. One of the big things is making sure that the water that goes through our plants is clean and it's got the right chemicals in there. And so I get involved in that too. So there's a lot of different aspects that come in. But I'm mainly focused in our downtown office and support the plants. Question? Anything else? Yeah?
How many different types of engineering? You said chemistry and
Different types. So we have mechanical engineers, electrical engineers, civil or structural engineers. Those are our three biggest ones probably. So mechanical engineers work with the pieces of equipment, the pumps, all that stuff. We have electrical engineers that handle not only the electrical cables and wires, but also the computer systems. There's lots of computers in a power plant that help make it operate properly in a safe manner. Our civil and structural engineers, they work a lot with the buildings themselves. If you go to a hydroelectric plant, the dams, the big pieces of concrete and steel and all that stuff, they get involved in that. Outside of that, we have chemical engineers, we have chemistry, people that majored in chemistry, on site specifically, making sure that the water quality is where we need it to go. What else? We have lots of technical people in welding and cutting and fabricating equipment and things like that. And then, like I said, environmental services. We have some interesting people there. A lot of people, biologists, geologists, archaeologists, all different types of people related to science fields that work for engineers. So it's a great question. Yeah.
What role would a biomechanical engineer play in PGE?
Biomechanical engineer. That is a good question. To be honest with you, I don't know. I have, yeah, I don't know. I'll be honest with you. I don't want to give you a wrong answer. But I do have some people that I know within the engineering field. I have a friend that does biomedical engineering actually, and he actually works on devices that they implant to help people that are dealing with chronic pain. They actually goes into the surgery rooms and helps the surgeons implant these devices that they've developed to help people with chronic pain. So engineering just in general can go into a lot of different fields. But unfortunately, I'm just very familiar with the power industry. So. Any other questions?
Last chance.
Yeah.
How often do you come talk to kids?
That's a good question. I like to do it at least once a year. This is my first time talking to an 8th grade class, but I've talked with elementary school students before, and yeah.